All right, welcome back. So in the previous video, we talked about, or we introduced the fundamental theorem of calculus part one and how we can use it to pretty easily differentiate certain types of accumulation functions. Accumulation functions, basically where we have a fixed lower limit of integration and a variable upper limit of integration. And it's super easy to apply if we have the correct form. Now, there are a couple different forms here. I'm going to talk about two examples where we have to do a little bit of manipulation either in the front end or the back end when applying the fundamental theorem part two. And here are those two scenarios. So the first here is if you have an accumulation function where the upper limit is a variable besides the identity function, usually x. But we could have a different independent variable like z or y or w or whatever. But the upper limit, at least initially, needs to be just a plain identity function. So what do you do if you have a situation like this? If you want to find the derivative of an accumulation function that's like from a to x squared of f of t dt. That's not how the fundamental theorem part one is set up. It's set up as if there's a plain x there. Now it turns out we're going to solve it in a very similar way, but we have to just do a little bit of extra work on the back end. So that's the first bullet point here. We have to be careful if there's anything up here except for an x, or I should say the identity function, in case the variable is in case the independent variable is not an x. Okay, we'll have situations like where, say, there's like a sign x up there, or maybe there's an e to the x up there. Again, we'll have to have special consideration if there's anything except for the identity function. That is the independent variable to the first power, by itself. Plain independent variable. Okay? Now, another situation that requires special attention is when the limits are reversed. That is, the lower limit is the variable and the upper limit is fixed. We usually call it a. So that is going to be a slight issue as well. Now that's a very easy issue to fix because we have the limit reversal property. But remember that is not how the fundamental theorem part one is stated. It's stated that you have to have a accumulation function of the form where the lower limit is fixed. Oh, erased a little too much. Where the lower limit is fixed, but the upper limit is variable. And if we have a situation like that and we want to take the derivative, well, we have a nice predictable solution, and that solution is the integrand evaluated at x. So let's take a look at the second situation. We'll take them in reverse order. So suppose we want to find g prime. That is, we want to find the derivative of this accumulation function. And notice the only problem with it, and it's a very minor problem, is the fact that the lower limit is variable and the upper limit is fixed. We want the opposite to be true. We want the lower limit to be fixed, i.e. in this case -3, and we want the upper limit to be the variable. So what can we do? Okay, well, we want to take the derivative of the right-hand side. Well, notice we have what we call the limit reversal property. The limit reversal property of integration said this. It says the definite integral from a to b of f of x dx equals the opposite of the indefinite integral from b to a of f of x dx. In other words, if we swap the limits of integration, if we transpose them, then we get a negative sign out in front of our integral. Okay? So we do that because that will give us now the variable upper limit and a fixed lower limit. And of course, once we do that, we can differentiate. I suppose technically we're using what's called the constant multiple rule of limits to factor a -1 out of our derivative. Because we can factor constants out of a derivative. That's a rule we've been using for a while now. We can factor out -1, and then we apply the fundamental theorem, which says we simply evaluate the integrand, which this is the integrand. We evaluate the integrand at x. So instead of square root t squared plus 5, we write square root x squared plus 5. And of course, we have the negative sign that comes along for the ride. So that's a very easy problem to fix. We simply apply the limit reversal property, and we make the upper limit variable while we make the lower limit fixed. Easy property. Easy problem to fix. Now the second problem, these aren't really problems, they're just the second situation, I should say. The second situation is when the upper limit of integration is a function that's not the identity function. So here, notice I have x squared instead of a plain x. So x is the identity function, x to the first power. X squared is not the identity function. Anything besides x is going to require special attention. So here's what you do. If you want to apply the fundamental theorem, you proceed as usual. Now, what does that mean to proceed as usual? Well, we evaluate the integrand. So here's the integrand. We evaluate the integrand at x squared instead of t. So notice I've replaced all of my t's with x squareds in parentheses, of course, to be careful. So I replaced all of my t's of the integrand with x squareds, but here's the new part. I have to apply the chain rule. The chain rule says we multiply by the derivative of the inside function. So basically, what I've done is I've taken the derivative of the outside function, that is, I get the integrand, t cubed divided by 2t plus log t. I evaluate at the inside function, x squared, that is, I replaced all the t's with x squareds, and here we are to the third step of the chain rule, which says we multiply by the derivative of the inside function, which of course the derivative of x squared is just 2x. So I multiply by 2x, and really the only thing left to do at this point, we're done with calculus, the only thing left to do at that point is to do a little bit of simplification algebraically. We know that x squared cubed, if you take a power function and raise it to another power, you multiply the exponents, so we get x to the 6th right there. But then we multiply by 2x, so that gives us 2x to the 7 on the numerator, and that's basically it. Okay, so if we're gonna have an accumulation function where the upper limit of integration is anything except for a plain x, we're going to have to apply the chain rule, which simply means we make our substitution and then we multiply by the derivative of the inside function. Okay? So let's look at a couple quick examples. And again, these go almost as quick as the previous video, but they do require just a little bit of special attention. So let's look at example A. Example A, we noticed what is the situation. The situation is we have a lower bound that's variable and an upper bound that's fixed. Well, if we want to apply the fundamental theorem of calculus part 1, well, then we need the opposite to be true. So I'll just jot down the theorem up here just to keep it fresh in our minds. We know that the derivative with respect to x of an accumulation function with a fixed lower limit and a variable upper limit of some function f of t dt, the derivative of that expression is f evaluated at x. So for part A, I simply need to apply the limit reversal property. So I'm going to rewrite the function first. So y equals, now if I transpose the limits of integration, if I swap them, the limit reversal property says I need to put a negative sign out front. And then the integrand remains unchanged. So square root of t times sine t squared dt. And now if I want to differentiate, I can find y prime. and I differentiate the entire right-hand side, which is the negative definite integral from -10 to x of square root t sine t squared dt. Now, I probably should note that we're going to apply the constant multiple rule of derivatives because I have a -1 right there, essentially. It's a negative sign, a -1. Well, we know that according to the constant multiple rule of derivatives, I can factor out a negative sign, a constant, and so I do so. And now I have exactly the form I need. I'm taking the derivative of an accumulation function where the lower bound is fixed and the upper bound is a variable, x. I know exactly what my answer is. It says it has a very predictable answer. I simply take my integrand here, and I evaluate my integrand at the upper variable x. So I get square root of x times sine x squared. Done. Now, I should say we don't have the tools to verify this answer, but we know that is the answer according to the fundamental theorem part 1. Remember, like in the previous video, I picked examples such that we could verify our answers by evaluating the integral and then differentiating. Here we can't do that, but we're guaranteed this is the answer according to the fundamental theorem part 1. Okay, let's look at example B. Example B does not have the issue of example A. Example A, we had the limits were swapped. Now the trouble, the little bit of trouble at least, with example B is the fact that we don't have a plain y up here. Now notice the independent variable is y. And usually like with example A here, the independent variable is x. Here with a B, the independent variable is y. I did that on purpose just so we're used to using different variables. Now, if we want to find h prime, well, h prime of y is equal to the derivative of that right-hand side. Now we're taking the derivative with respect to the independent variable y, so the derivative with respect to y of the definite integral from 1 to e to the y of natural log t squared dt. Now, all we have to do, at least initially, is evaluate the integrand at the upper limit of integration, which is e to the y. So here's the integrand, natural log of t squared. So initially, all we have to do is write natural log e to the y squared. So I replace the t with e to the y. But here's where we have to take a little special time, a special consideration. We've evaluated that derivative, and basically we're working with a composite derivative now, which means we have to apply the chain rule. So what I've done here is basically I took the derivative of the outside function, that was natural log t squared. I evaluated at the inside function e to the y. That's the first two steps of the chain rule. The third step of the chain rule is to multiply by the derivative of the inside function. So the derivative, and again, we're working with the independent variable y, so the derivative with respect to y of e to the y, like so. Now we get natural log e to the y. Okay, e to the y squared. Again, if we have, and I've mentioned this already once in this video, if you have like here exponents raised to more exponents, you multiply the exponents, and we get e to the y times 2, or 2y, times the derivative of e to the y. Well, okay, the derivative of e to the y, of course, with respect to y, is simply e to the y. The derivative of the natural exponential is itself. Now, we can do, it looks like one last simplification here. Algebraically, we can say that this first expression, here I'll circle it here in blue, that first expression simplifies nicely. Do you know how it simplifies? It simplifies simply to 2y times e to the y that was already there. Now, why does it simplify? Why does that blue section, why does that simplify to 2y? That's due to the inverse nature of the natural log in e to the x. From college algebra, maybe pre-calc probably, you had a property that says this: natural log of e to the x equals x, because natural log and e to the x are inverse functions. So basically, whatever's in the exponent of e to the x, the function simplifies to that. Likewise, there is another property. The other way is that e to the natural log of x also equals x. Those are called the inverse properties of the natural log and natural exponential function. So there we are, completely simplified 2y times e to the y. So that is the derivative h prime of y. Okay. Oh, and I should say back over here, that is y prime, our derivative. So, all right, last one. Now the last one exhibits both of our situations that require a little extra attention. Okay, so notice not only is the upper variable fixed, but the upper limit of integration fixed, but the lower limit of integration is variable. If we swap them, which we can do very easily, notice that the upper limit of integration will still be something aside from the identity function. It'll still be something aside from a plane z, since we're working with the independent variable of z here. So we're basically going to have to consider both of our situations that we just looked at. So let's see what we can come up with. Let's first rewrite f of z. Let's use the limit reversal property and just do this. Say f of z equals, now if we swap the -2 and the arctan 5z, we have to introduce a negative sign out front. So we put a negative sign there, and we put a -2 now as our lower limit of integration, and the arctan 5z is now our new upper limit of integration. And that doesn't affect the integrand at all. 1 over 1 plus x squared dx. So now I've just applied the limit reversal property. Now at this point, I can take the derivative. So I want to find f prime of z, the derivative of f with respect to z. This is going to be the derivative of the right-hand side with respect to z. So we have a negative out front, and then we're going the definite integral from -2 to arctan 5z of 1 over 1 plus x squared dx. Okay. Now, I go to do this. The first step I need to do is to factor out that negative sign. So that's going to be using the constant multiple rule of derivatives. So I factor out a negative sign. This is a very easy step. And then I have the derivative of the definite integral from -2 to arctan 5z 1 over 1 plus x squared dx. Now, at this point, I can apply the fundamental theorem. I do so by evaluating the integrand at the upper limit, which is arctan 5z. So here is the integrand, 1 over 1 plus x squared. So I evaluate that at arctan 5z. So we get 1 divided by 1 plus arctan 5z squared. Like so. So that's, I've evaluated the integrand, f of x at f of the upper limit, which is arctan 5z. But because I plugged in arctan 5z and not just a plain z, not just the identity function, I have to multiply according to the chain rule. That is, I have to multiply by the derivative of the inside function. So we multiply by the derivative with respect to z, since that's the independent variable, of what? Well, of arctan 5z 5z. Now, notice that arctan 5z is itself composite. So I'm in the middle of applying the chain rule, but now I have to apply the chain rule again because arctan 5z is composite. So what's the outside function and inside function of arctan 5z? Well, I think the outside function is arctan z, and the inside function is 5z. So, oh, you know what I forgot on this step right here? I lost my negative sign. So I need to put that right there. I left the negative sign. Sorry about that. Fixed now. Better late than never. And so now I can, let's see, what can I do? I can write that first fraction is still just negative 1 over 1 plus arctan 5z quantity squared times the derivative of arctan 5z. Now, the derivative of arctan 5z, like I said, requires the chain rule. So what's the derivative of the outside function arctan? Well, the derivative of arctan is 1 over 1 plus x squared. Okay, that's the derivative of arctan. We then we then evaluate at the inside function. So the inside function is arctan 5z. Squared like so. So that's the derivative of arctan. That's the first step of the chain rule. Evaluated at the inside function, 5z. Oh, sorry. What am I? I'm getting confused here. Sorry. The derivative is 1 over 1 plus x squared. We then plug in the inside function, which is a 5z. So I have, sorry about that. I plug in a 5z squared. Okay, there we go. That's the derivative of the outside function, arctan 1 over 1 plus x, or in this case, z squared, 1 over 1 plus z squared. I then evaluate at 5z, so that gives me 1 over 1 plus 5z quantity squared, and then I multiply by the derivative of the inside function, 5. Okay? So if I want to write this, basically there's not a whole lot to do simplification-wise. I simply get a really big fraction bar. That's called a vinculum. On the top I have a negative 1 times 5, so I'll just put a negative 5 up there. And on the bottom I have 1 plus arctan 5z squared, and then I multiply by another set of parentheses, 1 plus 5z squared. That could be rewritten as 25z squared, like so. So there we go. There is f prime of z. That is a big, somewhat ugly derivative. But it's predictable, at least. It wasn't hard to come by. We just simply had to apply the chain rule actually twice there, and we had to apply the limit reversal property. So again, anytime you don't just have a plain situation like this, you know, if you have that situation, the fundamental theorem part 1, super easy. Just your answer is f of x. Replace the replace the dummy variable t with the independent variable x. You're good to go. But if you have either of these two minor situations, then you'll have to do a little bit of rewriting, either at the start using the limit reversal property or at the end using the chain rule. Okay? But it's important that we're looking out for these situations because these will happen fairly often. All right, we'll do a few more examples in the next video. If you have any questions in the meantime, feel free to reach out. Otherwise, I'll catch you in the next video.